Hello students, welcome back. I am Wasim, your teacher for Analytical Mechanics Numerical Practice class. Until now, we have practiced the selective problems from chapter 1 to chapter 4. Based on the syllabus, chapter 5 is remaining, which will be covered in the coming few video lectures. Last week I gave you an option to tell me the number of problems which are still challenging for you. I am surprised to know that only one student is facing difficulty in solving problems. Anyhow, one of the students requested me to solve problem 2.15, problem 2.14 and 3.25. In this video lecture, I will solve problem 2.14 and the problem 3.25 will be solved in the coming video lecture. Regarding the final exam, I am planning to give you take-home exam because of the corona pandemic. First I will cover the chapter 5, then I will design the final exam. Now I am going to solve problem 2.14 for you. The statement of the problem can be seen on the screen. A particle of mass m is released from rest or distance b from a fixed origin of force that attracts the particle according to the inverse square law. Force is equal to minus k over x square. Show that the time required for the particle to reach the origin is pi into mb3 over 8k square root. So we will start from Newton's second law, which is max is equal to summation of fx. This is one-dimensional case. So as given in the problem, this equation is given in the problem, like fx is equal to minus k over x square. Putting this in equation 1, this is equation 1, we will get max equal to minus k over x square. This is equation 2. And we know that the acceleration is equal to rate of change of velocity. We can write acceleration in this form: ax is equal to dv over dx dot dx over dt, which is equal to dv over dx dot v. So equation 2 becomes, this is equation 2, it will become mv dv over dx. We only replaced ax because ax is equal to dv over dx dot v. So this term is here now. So mv dv over dx equal to minus k over x square. So we can say like it is k over x square, like k over x square. Sorry, my writing is not good here. This is k, or simply we can say that minus k x power minus 2. Both are same. So integrating this equation, above equation, with separation of variables, we will get, with separation of variables, it is v dv integral from 0 to v equal to minus k over m integral of x minus square dx. So because this is very simple integration, you note that these are the results, and with more simplification we will get v square over 2 equal to k over m into 1 over x minus 1 over b. From here v square is equal to this term, and then v is equal to square root of 2k over m into b minus x over xb. This is equation 3. As mentioned in the previous slide, v is equal to dx over dt, rate of change of displacement. So equation 3 can be written as, this is the equation 3. So when we replace this velocity with dx over dt, so equation 3 can be written as in this form: dx over dt equal to square root of 2x over m dot b minus x over xb. So we will integrate this equation, like from b to 0. You know that it is given in the problem that the particle moves from rest to distance b. So when it is at rest, so it is 0. When it moves to distance b, so here it is b. In 0 to t time, in time t, it moves from 0 to b. So we just separated the variables and integrated it with respect to the conditions. So this is final equation 4. So now we will integrate the left hand side of equation 4. This is the left hand side of equation 4. So from here onward, it is very simple integration. I name this equation as a 4a because we need this equation in later stage. So in the previous equation, there is one term which is square root of b minus x over x. So we for simplification, we say that z is equal to square root of b minus x over x. This is just for the simplification. So when we take derivative of z dz, so we get, this is very simple basic derivation. And with simplification we get this result. Yeah, this is with more simplification. So here you can see this is the term which is square root of b minus x here also. So from this relation, from this relation we can say that b square root of b minus x is equal to zx. So we will simply replace this term. Here we replaced square root of b minus x with z square root of x here also, and this is the more simplified form. So finally we get dx is equal to, with simplification, finally we get dx is equal to 2xz dz over z square plus 1. So I name this equation 5. As square root of b minus x is equal to z square root of x, so from this relation we can get the value of x here. So x becomes b over z square plus 1. So in the previous equation, I think that was equation 5. So we will replace x with this term. So putting this in equation 5, we will get dx equal to minus 2bz dz. So here it was x, so we replaced it with b over z square 1 plus 1. So here you see this is the square because of this term. So putting value of square root of x over b minus x and dx in equation 4a, this is equation 4a. So when we put the values of these two terms, this term and this term, finally we will get this equation: square root of mb over 2k integral b to 0 square root of x over b minus x dx equal to square root of mb over 2x integral b 0 1 over z into minus 1 2bz dz over z square plus 1. So this z is cancelled with this z. So finally we will get this equation, which is equation 6. Now solving dz over z square plus 1 is using reduction formula. So we will solve this term, integral of this term, with the help of reduction formula. So here I mentioned the reduction formula. So if we put a equal to 1, so this is a. If we put this term equal to 1, b equal to 1, and n equal to 2, so we will get these two terms. So previous equation, I think it was equation 6. So with the help of reduction formula, we will get square root of we will get integral of dz over z square plus 1 whole square is equal to z over 2 into z square plus 1. So these are the conditions, boundary conditions, plus 1 over 2 integral of dz over z square plus 1. So here it is simple integration, it is very basic. So substituting back to equation 6, we will get so this is actually equation 6. So you know that we solve this integral, so we will simply substitute its value in equation 6. So finally we will get minus square root of mb over 2k into integral of 2b dz over z square plus 1 whole square. It is equal to minus 2b square root of mb over 2k into z over 2 into z square plus 1 with boundary conditions plus 1 over 2 arc tangent z b0. So this is the simplified term. Changing boundaries for substitution by z, we will get this value, this term minus 2b square root of mb over 2k into, you know that here the condition is 0 to minus infinity. So this term, in both cases it will be 0, like in infinity or in 0 it will be 0. So only this term is remaining, 1 over 2 into minus pi over 2 minus 0, because tangent, because of this tangent. If we put these values, so we will get minus pi over 2. So finally, after solving the integral, we get this form. So left hand side, we have solved this, the left hand side, which is equal to pi square root of mb3 over 8k. Putting back this to equation 4, this is equation 4. So we will get simply this equation. So equation 4, in equation 4, so this term is equal to integral of dt. So here we simply wrote the value of this term. So pi square root of mb3 over 8k, it is equal to 0 to t dt. So this term is equal to t minus 0, here you see. So finally we get the time t, which is equal to pi square root of mb3 over 8k. So the time required for the particle to reach the origin is pi MB3 over 8k square root. So here I think I misplaced the square root here. So this is square root. Okay, thank you.